Okay, pizza fanatics out there and those of you out in Etherland, welcome to today's installment of the Mac Club. I am very pleased to introduce Killian Davis, who I've known for quite a bit. In fact, I met him in the Mac Club so many years ago, who is going to talk to us about topology, homology, and the Mississippi River.
All right, first things first, so people on Zoom can see, I'm going to share my screen. Here we go.
Oh, let's make sure. Why don't you ask them? We'll start the video there. Oh, it's not. And make sure they can hear us.
All right, hey, can you someone give me like a thumbs up or something to let me know if you can hear me? All right, stop everybody gave a thumbs up. All right. This works.
You should. Ask somebody if they want to control your camera.
Oh, back to my oh. There you go.
Well, you could actually ask somebody out there in either lane to control your camera.
Or if someone out there in either lane wants to control my camera. Just take us now. I don't know. Probably not. If they can see my screen, it should be okay. Then, all right, cool. All right, hello everyone. My name is Kelly Davis. I'm a senior here at Clemson, and today we're going to talk about topological data analysis and how that relates to the Mississippi River. So what we're going to be going over today is first, we're going to justify why we would want to use TDA, topological data analysis. And then after that, we're going to talk about 3 different algorithms that are common in the field. We have persistent homology, the mapper algorithm, and then we also have topology and time series. So that's a more recent algorithm, and it's a way to detect the period, or if the period exists in a time series, and if so, what that period is. And then I'm going to talk about how this all applies to ecology and the work I did over the summer. So moving on, what is topology first, generally, for those who aren't quite aware? One way to view it is like the study of the shape of sets. Now that's a little fluid and a little ambiguous. But if someone doesn't have a math background, I like to tell them it's kind of like geometry. So you don't care about distances and angles, so you're allowed to morph things, do things like that, but you're not allowed to rip or tear or glue holes together. All right. And then if someone has a little bit of a calculus background, I tell them it is the study of generalized continuity. And that is, when I took topology my sophomore year, that is how Dr. Burr phrased it. It is the generalized study of continuity. So we have different ideas of distance. How we talk about distance, or how we talk about continuity, we have different ideas of distance. And what happens if we don't have a well-defined notion of distance in a set? How do we talk about continuity then? Those are all questions topology deals with. So continuing on, what separates topological data analysis from, say, statistics, right? What different niche do these two occupy? So statistics more so describes the attributes of the data. So that, I mean, you talk about mean, median, mode, range, variance, all that. You could do hypothesis testing. You could do all those nice things. But it doesn't tell you very much about the shape of the data. And that's what TDA handles. It is primarily concerned with topological features or the general shape of the data. So the number of loops in the data, the number of connected components, the number of voids, and by a void, think like a sphere, a hollow sphere. The fact that the sphere is hollow, that's the void. And then it also handles high-dimensional data very, very well. So if, say, you're working in like 10 dimensions, that could be hard to deal with a little bit with standard statistics. Now, I'm not an actual stats person, so I'm sure there are ways to handle it, but requires more advanced tools, whereas TDA kind of out of the box is able to deal with it. And it answer questions like how prevalent different features are throughout the data. Like, if we got if the data is shaped like a circle, then a loop is going to be really prevalent. See that. We could also talk about how the data clusters. So maybe part of the data, like over here, is a little more. I don't know if they can see me very well. Is a little more dense than the data over here, and TDA is going to be able to help pick that up. So, that being said, here's kind of a rough example on where statistics and TDA might go. All right, and it's entirely made up. So, say temperature in Colombia follows like a cosine wave annually, right? So it peaks in the summer and it dips in the winter. Whereas the monthly rain totals might follow more of a sine wave, where it peaks in the spring, but it dips most in the fall. So, how do the two correlate? So you do something really simple. You plot the two out. The way I set it up, that's going to make a circle. Okay. You start to think of like your basic statistics. How do you handle this? Right? What does it mean to take the line of best fit of a circle? What does it mean to talk about the mean and the mode and the variance of a circle? And it doesn't mean very much, does it? TDA, however, is able to give you the tools that can study data shaped like a circle. So that's kind of the basic justification on why we might want to have something like TDA to handle these things. Continuing on, went the wrong way. No, it didn't. All right. Now we're going to talk about persistent homology, all right, which is going to be our first algorithm in the out of our three. So first, everyone I think knows what persistent means. All right. How long does it last? What is homology? Well, first, loosely speaking, homology is going to describe the number of connected components, the number of holes, number of voids, etc., in your space. Okay? If you have a little bit of abstract algebra in your background, what homology really does in a more general sense is it measures the exactness of a sequence. All right? And then this is all part of a field of math called algebraic topology, where the tools from algebra, such as groups and rings, act as like ways to like bookkeep different topological features. And so you have the topology that interacts with the algebra in a very specific way. You can prove things in the world of algebra and then send the results back to topology and vice versa. So sometimes it's really easy to prove things in algebra land that's really hard to prove in topology land. And sometimes it's the other way around. Algebraic topology kind of gives you the language to communicate back and forth between the two. So right here, I just have an example of a torus. A torus is like a donut, so to speak. So you're going to read this from right to left. So that first Z at the very end, there's only one of them. So that's actually going to tell us there's one connected component. And the two Z's right here, that tells us there are two distinct loops in the torus. So there's the one that goes like on top of the donut, and there's the one that goes towards the hole of the donut. And those are actually distinct loops. You can't morph one into another. And then that third Z right there, that actually tells about the void. So this is a hollow donut, which is kind of lame. But you imagine your torus, and there's actually nothing inside. That's where the void comes from. All right, and that accurately describes the homology of the torus. So homology is actually, well, I'm not going to say it's easy to compute, but there's an algorithm to compute it. It's kind of hard to understand, especially like the first time you're doing it, but it's something I can tell a computer to do, and it'll be able to do it. Different things in topology, such as the fundamental group, a lot harder to do in like general homotopy groups. There's not really a way to do that. You got to be more clever, but homology is more just an algorithm. So, that being said, persistent homology is how you talk about the shape of data. So, imagine plotting your data in whatever dimensional space you're in. So, maybe it's 3-dimensional space. All right, you plot all those points. What you're going to do is for every point, you're going to start drawing a bubble around it. Okay? Or an epsilon ball, if you're familiar with that terminology. Then we're going to construct something called a Rix complex. Okay, so for every bubble, if bubbles pairwise intersect, you draw the corresponding complex between them. So if it's just 2 bubbles, you draw an edge. All right, if it's 3 bubbles and they all pairwise intersect, you end up drawing like a triangle, and you actually you fill in the shape. All right. Then if you have 4 points, right, and maybe the top 2 pairwise intersect, the left 2 pairwise intersect, the bottom 2 pairwise intersect, and the right 2 pairwise intersect, diagonals do not, well, you get a loop, right? You don't fill in the middle. You just have 4 edges, and that makes a loop. Okay. So here is an example. Okay. And you guys get to see my GeoGebra skills. First, just a simple example. We plot 3 points. Okay. Then we start with small balls around each point. None of them are intersecting. Okay. Then as time goes on, the balls get bigger. When they do, when A and B intersect, we draw that edge. Okay, but notice A and C still aren't intersecting, so don't draw an edge. And as we continue, now A and C intersect, so we keep that edge stays, we draw a new one. So actually, if I go back real quick, we might see right here, we have 3 connected components. That's what's existing right now. As time goes on, one of the connected components dies. Now we only have 2. We have that point right here and that one right here. And then as time goes on, now we only have 1 connected component. And then finally, as the balls get a little bit bigger, everything gets filled in. Okay, so that's kind of a simple example with 3 points. If we had 4 points, like say 1 at the point 2, 1 up there, there might be a time where it makes a loop, right? And then as the balls get bigger, that loop will eventually be filled in. All right, so how do we measure now everything I just described? Like, is there a nice way to look at it without just having to stare at a bunch of diagrams? Well, we could summarize everything in something called a persistence diagram. So this measures the birth of some topological feature. So these are this is the 0 homology group, the first homology group. Remember earlier, 0 corresponds to connected components, 1 corresponds to loops. Okay. And it plots the birth minus the death. So this is our example data right here. All right, you see it looks like a loop. Okay. I run the persistent homology diagram or persistent homology algorithm on it. And you see we have a lot of connected components at the very beginning. Right, those are these blue dots right here. And very quickly they all die, right, at the very beginning, because they all kind of get smashed together. And then once they all die, this orange dot appears. Yeah. And we see because this line y equals x is when birth equals death. So the closer it is to this line, the less significant it is. So farther away it is from the line, the more significant it is to the data. So with this loop right here, we see that there's that loop, and it is quite significant because it is far away from the line where birth equals death. So it's born, and it stays a long time before it dies. Does that make sense to everyone? Okay, I'm getting on. So cool. All right, so that is persistent homology. Now we're going to move on to a more complicated algorithm called the mapper algorithm. And this is actually primarily what I use over the summer. So I'll talk about it, then I'll come back to it later. So the goal of the mapper algorithm is to turn the topological space or point cloud data that we've been talking about into a simplicial complex that is easier to handle. So a simplicial complex is like you have points, you can connect them with edges, you can connect those with hedrons and keep going higher and higher dimensions. Yeah. It's essentially a really nice shape that's easy to work with. So this is example data. Okay. Notice we have the loop with a stick coming out of it. I run it through the mapper algorithm, and I get a loop with a stick coming out. Okay. So what this is able to do is it's able to draw a simpler shape while preserving important topological features. In this case, the loop with the stick. Right. And it's actually able to do this while turning high dimensional data in the lower dimensions while preserving our important topological features. So how does it actually work? Well, here's here's it kind of spelled out in rigorous terms. All right, and then I'm going to show you a nice picture to summarize it. We're going to define a filter function from our point cloud of data to some parameters. So, for example, we have maybe 10-dimensional data. We're going to cast it down into 2 dimensions. Okay? So we could think about projecting onto maybe the X and the Y axis, right? The first axis and the second one. Or you could do something called principal component analysis, right? And get the vectors, the axes that are most important for explaining the variance of the data and project onto those, right? So essentially you plot your points, principal component analysis will tell you the direction where most of the data is laying, and then you project onto that axis. That's a very common filter function. Then you're going to define an open cover, all right, on your image. Okay, and it's important that these are more like overlapping bins, all right. And then you run a clustering algorithm on the data, right? So you look at each, you look at the pre-image of each bin. You run a clustering algorithm on it, and that takes place of your connected components. All right, so something is, we think of clusters as connected components pretty much. And then you're going to construct the nerve of the pre-images, and I'll go over what that is. But essentially, loosely speaking, the idea is each cluster is going to become a node, all right, a point. And then, so remember when I said the bins are overlapping? So 2 clusters actually share points. You draw them between the 2. All right, and then that's how you construct the simplex. And there are ways to generalize it, and so it works in more than just a 1-dimensional simplex. But we're just going to focus on the 1-dimensional stuff for now. So, nice picture that Shannon Bullock made. So, this is actually from a paper talking about coronavirus and using the mapper algorithm to handle that. But anyway, we have this data shaped like a fish. Okay? We're going to project that onto the x-axis. So that's our filter function, projecting onto the x-axis. Okay? Then we're going to construct our open bins. All right? And then we're going to look at the pre-image of those open bins. Now you might ask, all right, for a computer, how do we construct the open bins? Essentially what you do is you define the number of bins you want, and then the percent overlap for each bin. Okay? And so now the next question is how do you choose the number of bins that you want and the number of connected, or in the percent overlap. And if you're able to answer that question, congratulations, you now have a paper that you can write to get a PhD. There's not a way to do it. You just kind of got to try a bunch of things and see what persists. That being said, you have, say, the red bin right here, the points that go into it. All right. Notice that overlaps with the green, blue, the teal looking bin. All right. And notice there are points that are in both. Okay. So we run our clustering algorithm down here. All right. So this red bin only has 1 cluster. All right. But you notice, you see those 2 points right here? Those 2 points also show up in the green bin. Okay. So those 2 clusters overlap. All right. And we look at the green bin, we got 2 connected components. Okay. So now I go into drawing the picture. All right. So the red cluster becomes a node. All right. And there is overlap between the red cluster and the top green cluster. So we draw an edge. And then the same thing going on at the bottom. There's overlap between the red cluster and the bottom green. Right? There's a point common between the 2. So we draw an edge. Same thing for the 2 green clusters and the purple cluster. All right. You just look right here, actually, in the top right corner. The pre-image, or the green and the purple overlap. There are points common in between. So we look at the pre-image, right? And there's a single cluster in the purple, and it overlaps with both the top green cluster and the bottom green cluster. So those both get edges. Then same thing with the tail. All right. Tail ends up going into 2 clusters. Both overlap with the purple cluster. So we draw it. Make sense? Everyone's following? Cool. That is the mapper algorithm. All right. Here's another example. I'll go through it a little more quickly. We got a hand, all right? Point cloud data shaped like a hand. Okay. So we're gonna our filter function is actually, in this case, it's just the x value, right? So so to the left it's red, to the right it's blue. So reds are lower values of x, blues are higher values. Okay. And then we define our open cover, and we look at the pre-images for each open set in the open cover, each thing. And you're going to notice that there's some points like at the tip of the finger that are also found at the other side of the tip of the finger. They overlap, so we're going to draw all the way. So we have 3 clusters right here, 3 nodes right here. Those overlap with the 3 right here, so they get an edge, but not the pinky. So the pinky does not get an edge. Make sense? All right, and then same here, we got this one. We actually only have 1 cluster because all the fingers connect without the palm, except for the thumb. Actually, so we have 2 clusters. Remember, this isn't 3D, right? So we got the thumb right here. That's not connected to anything, along with that yellow bit. All right, and then we have just the palm, and then the thumb connects up, and then the wrist. So that is how the mapper algorithm, for example, takes 3-dimensional data and packs it down into, well, in this case, the 1-dimensional simplicial complex. Following? Cool. All right. So much for the mapper algorithm. So on to topology and time series. So this is going to be from a paper written in 2019 that I finished working through about a month ago for the work I'm doing. So what the goal of this algorithm I'll present to you that still doesn't have a name is we're going to detect that the time series is periodic. Okay? And then if it's periodic, we're going to detect the period. And then we're also going to detect if the period changes at all. And we want it to be robust with noise. So if you aren't familiar with the time series, you just think about the daily high temperatures and Clemson throughout the year, right? It's just time and plotted over time. Okay. Another one is the stock market. All right, we're going to look at the graph of the stock market. That's a time series. Okay. And there are other algorithms out there that exist for doing this that are more analytic in nature, for example. But this one I'm about to present to you, at least the paper I read, argues is more robust to noise and actually requires less data to predict the period. So let's go through it. All right. First, we got to talk about the sliding window embedding. Okay. So we're going to let f be a function that gives us the time series. All right. So, for example, if x naught was a week ago, and f naught is the high temperature in Clemson a week ago. Okay, and then maybe xk is today, fk is the high temperature today. Okay. Then the sliding window embedding is essentially a vector from the time series with equally spaced apart points. So if you take it n, all right, and then your vector is going to be in r n plus 1. And then d is how spaced apart they are. Okay. So, for example, all right, this is our time series, right? So first entry is 10, second entry is 20, so on and so forth. All right, I only care about the y values. So for n equals 1 and d equals 2, our sliding window becomes 10, 30, right? So I start at the beginning, I go 2 over, 20 and 40, 30 and 50. And I can plot that in R2. Make sense? Okay. So if our time series is periodic, then actually plotting the sliding window embedding is going to make a loop. All right. We can use persistent homology, which we talked about before, to detect the presence of a loop. All right. And then turns out that the presence of a loop in the sliding window embedding is necessary but not sufficient to conclude that the time series is periodic. For example, all right, say we have a sine wave. Okay, we have the positive part of the sine wave, the negative part of the sine wave, right? Consider a function that follows that sine wave. All right, we have 1 positive part, 1 negative part, 2 positive parts, 1 negative part, 3 positive parts, 1 negative part, so on and so forth. That will make a loop. It's actually have a little bridge connecting right there, but it'll make something that looks like a loop, but it's not periodic. So how do we, so we need to do more essentially, and to do that we talk about Voronoi cells. So I learned something cool about Voronoi cells today actually, is that they were used to help show that the cholera epidemic in London is actually related to dirty water. So essentially what the guy did was he drew Voronoi diagrams of water pumps in London and where the cases were. Sure enough, they lined up with some water pumps. He was able to show that it's a Voronoi diagram.
When was that? Well,
Like 1860 or something. But essentially the idea of a Voronoi diagram is you pick points and then in your space, you assign each point to the closest to the center points that you picked earlier. So for example, we have a circle, all right, and I picked 4 points. And then each different color corresponds to the Voronoi cell. So the red is A. I guess this color doesn't show very well, but then the more blue over here corresponds to B. All right. And then we're actually going to do that on the sliding window embedding. So we're going to pick however many equally spaced points that we want. You could use that using either K-means or min-max algorithm. Essentially, sklearn takes care of that for us. And then we're going to construct the Voronoi cells with those points. The reason we're doing this is because if you have noise in your data, then it doesn't make sense to use the rigorous definition of periodic, right? Where f of t equals, or f of x equals f of x plus t, right? We need a softer definition. And that's what this Voronoi cell thing offers, is that instead of looking at for exact equality, you look at, all right, as this progresses, does it get close to where it was before? That's why we do this diagram. So for each Voronoi cell, we're going to measure the jumps in the time series, and then we're going to verify that the dominant jumps are equally spread. If they are, it's periodic. We can conclude they're periodic. And then we're going to verify that the average spread, and then the average spread is actually a proxy for the period for that Voronoi cell. Then we take all those proxies, average them, and that's our estimated period. So if we go back to our circle, all right, because that sounded like a lot. Imagine we're just marching along the circle in our time. This is our sliding window embedding. We're just marching along the circle. Okay? Maybe we have a nice, very nice time series. We have 10 in section A, 10 in section B, 10 in section C, 10 in section D. All right? And it's all, so we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the jumps are 1, 1, 1, 1, 1, 1. So we get to here, right? Then the jump is going to be 30. We got 10 here, 10 here, 10 here. So 30 is that dominant jump. We keep measuring that as a 1, 1, 1, 1, 1, 30, right? And we see that the 30s are each 10 apart. So they're equally spread. Okay? And then 30 serves as the proxy for the period for this Voronoi cell. We do that for every cell, and then we average that together, and that is our estimate for the period. There's a little more out there, a little more complicated. Does that make some level of sense? Okay, I'm getting a few nods, so I'm going to continue. All right, and that picture right there is just a nice summary. We have our time series, sliding window embedding. We look at the persistent homology diagram, and then if we're looking at a subset of the data, we look at the norm, right? But I'm not going to worry about that at the same time. And we pick our landmark points, construct the Voronoi diagram, and then we do what I just described to you, which is called symbolic dynamics, is what they call it in the paper, and we extract the period from that. So let's see a few examples. How well does it actually work? Well, here's a regular sine function, period time. All right. I ran the diagram, and there's not a package for this. So I don't mean to brag, but I had to write the code. And I don't write like, I mean, I used sklearn, but means and things like that. But real period is 10. Period I got estimated was 9.77. Pretty good. All right. So I just used the inputs were from 1 to 10.01 apart. So it was a pretty big time. And then actually I think that's supposed to be a number. Oops. And then I used n equals 30, so I used the 30 dimensions. or I guess R31, and I had them spaced 8 apart. And I used 30 Voronoi cells. I could have gone smaller, but I was just looking for an example, so I just did 30 and 8, and it worked, so I just moved on. But the persistence diagram, that's very significant. That's by far away from Logical's X, isn't it? So it's all nice. So cool, it works for nice clean data, but the world isn't nice and clean. So what about if I have the same function, but now I introduce uniform noise? For each point, I add a random number between 0 and 1.5. Now keep in mind the amplitude was 1, but the sine function was 1. And so I'm potentially more than doubling it, right? Which is quite a lot of noise. All right. This is what the time series ends up looking like. This is what the persistence diagram ends up looking like. So so the connecting components are a little bit more significant this time. But we still have the single dominant loop. These are a bunch of smaller loops ended up forming, but they are all close to y equals x. I could pick one. Okay, we have a single dominant one. All right. I ran it before. The estimated period was 8.66, which isn't bad. I couldn't actually tell you what the real period is because I ran up noise in it, but it's going to be close to 10. So 8.66 isn't awful. Moving on. What about if our time series changes? Does it still work? All right. So for 0 to 3, I'm just taking, I didn't introduce noise, but I'm taking cleanly from just the regular sine function. So it has period 2 pi. Then from 3 to 7, I take from a sine function that has period 10. And then from 7 to 10, I take from the sine function that has period 5. Will this algorithm detect all 3? How can we modify it to do so? Well, what I did was, instead of looking at the whole thing, I just looked at a subset of 250 points is what I picked in this case, and just slid it along and ran this algorithm for each of those subsets and had it report back to me the estimated period. And so I used, well, I ended up decreasing the dimension this time from n equals 10, then d equals 4, and I still use 30 Voronoi cells. And here's what we get. All right. So this beginning part right here, where it's predicting 0, is actually, it's not using all 250 points. Right. So like right here, maybe it's using like 25 points. And that's not enough to detect the periodic behavior, so I just had it return 0 if it failed to do that. Then once we get a little bit more than 100 points going in, that's actually enough to detect the periodic behavior. So that's about 1.5 periods. Okay, and it shoots up, and it gets a little bit more than 6. So that's pretty good, pretty accurate, right? Because right here, period is 2 pi, and then about at 300 is where it's going to flip, right? And so there's a delay, and if you look back, actually, this delay is quite significant because look how big that jump is. It's quite discontinuous. Okay, so there's going to be a delay, but it still picks up. It takes a little less than 10. It still picks up that period. And then if you look back again, there's still a discontinuous jump, but it's much smaller that time. I'm going from 10 to 5, and it's able to go down and predict the 5. We've now found all 3 periods in our time. All right. Finally, we're going to talk about ecology. So I had an RU this summer with the University of Wisconsin-La Crosse, and we worked closely with the United States Geological Survey to study the ecology of the upper Mississippi River. Okay, so they've been, if you guys ever have a chance to do an REU, do it. La Crosse is, they're asking for an extension for their REU, or they're a new grant in the ISF. That's what I'm looking for. So if they end up getting it, you should definitely apply to La Crosse. It was a lot of fun. It's a beautiful area, and Wisconsin has really good cheese. So, that being said, long-term resource monitoring data set is a data set that the United States Geological Survey has been collecting since like 1993. Okay, and they collect a lot of water quality and chemical information about the Mississippi River and some of its tributaries. So big Mississippi River system. Why do we care about that? Well, the Mississippi River is a major trade route. It literally connects the heart of America. And it's also ecologically, it's the longest river in the world. And also just the Mississippi River basin is gigantic. I think if you just drive a little bit west from here and get to Tennessee, dump some water on the ground, that water will find its way to the Mississippi River. I don't think right here. I think right here it goes into Lake Hartwell and that finds its way into the Atlantic. All right. So the Mississippi River basin is gigantic and it covers a lot, a big part of it. It reaches like all the way over to like Nebraska. All right. So the first thing I had to do with this data was actually clean it up because there was a lot of missingness in the data and it wasn't random. So things like measuring the total amount of phosphorus in the water is expensive. So they didn't do it for every sample. They only did it for certain samples. But we can interpolate for that, right? We're mathematicians. We know how to. Well, we like to think that we know how to handle things like missing data. So that's actually what we spent the first few weeks of the RU on, was instead of just throwing out 80, 70% of the data, let's actually try to fill it in and see what we can get. So we tried a bunch of different methods. I worked on inverse distance weighting. So that's a spatial interpolation, right? So use points nearby to interpolate the points nearby is the idea. And there was also tried polynomial, and then we did random forest. And random forest is the one that ended up outperforming all the others by our error metrics, and that's what we went with. And hopefully now we wrote a paper about it. Hopefully it gets accepted. So they collect data from central Minnesota, it's kind of where it starts, all the way down to Cairo, Illinois. No, I'm not pronouncing that one. It's called Cairo, Illinois. That's at the very bottom of Illinois. All right, Illinois is the long shape. I've had too many people here who think Indiana is Illinois and vice versa. Illinois is the long one, okay? All right. And Cairo is at the very bottom. Illinois has a lot of towns named after places from across the pond, and they're all pronounced wrong. All right. Right next to where I'm from, Springfield, is Athens, Illinois. Right. We also got Berlin. Not Berlin, it's Berlin. Okay. So we collected data from all those areas, Mississippi and the Illinois River. And we have about 150 variables that we measure. A lot of them, some of them are like quality check variables and things like that. But in that data set, we actually have 11 continuous variables. They are water depth, Secchi depth, which is there's something called a Secchi disk. And it's black and white, and you stick it in the water, and when you can't see it anymore, that's the Secchi depth. All right. Secchi depth, velocity of the water, temperature of the water, turbidity, which is another measure of water clarity. So they take a sample, they shine a laser through it, and like the amount of light that gets through is turbidity. A little different than that, but that's pretty much it. Suspended solids, which is exactly what it sounds like. They take the sample, boil off all the water, measure the mass of what remains. Little phosphorus, little nitrogen, full chlorophyll, dissolved oxygen, and conductivity. All right, and we define an ecological states to be a bundle of water quality and chemical data that persists through time. All right, and then not much is known about big river ecology, actually, which you think there would be, but I was surprised to learn there's not. And that's because it's a very complex system. That makes it hard to quantify with things like standard statistics. And so ecologists have lots of these hypotheses about big river ecology. For example, for ecological states, it's hypothesized there's a clean water state and a turbid water state, right? And so far, ecologists have kind of just seen these with their eyes. Oh, I can see through the water. All right, it's clean water. Oh, it's covered in algae. All right, that's turbid. All right. You think of turbidity almost like how much algae there is. Okay. And there's also an hypothesized third state called the groundwater state, where it's so bad that not even algae is going to fit. Okay, so these different states are important because they actually determine what type of life can live there. Okay, so clear water can have very diverse life, right? All types of different plants and animals. It's taken over by algae in a turbid water state. That's not going to happen. It's actually very toxic, especially when the algae dies. Okay, that releases a lot of bad chemicals in the water that kills lots of things. So, and then groundwater state, it's not even algae that live there, so really bad. So, ecological states also change over time. Okay, and they change quickly. By quickly, I mean one day it's clear water, the next day it's turbid. But they tend to be stable, right? So if you imagine like valleys, okay, they are at the bottom of the valley. In order to change, you got to push it up over the hill, and it'll fall over the hill and go to the next valley. All right, that's kind of one way to think about ecological states. But how? This leads us to actually our research questions. How do we quantify ecological states? What are the ecological states in the upper Mississippi River? How many are there? How have they changed over time? The three questions we attempt to answer, right? So we have pool 4 here, up in pool 1 is actually up in central Minnesota. Pool 4 is north of where I was, and then there's pool 8, which is actually where I was over the summer. That's right by La Crosse. It's actually a pool that's on Alaska, Wisconsin. Wisconsin also has a lot of fun names for their prawns. Then it goes down to pool 13, right? And then right here is actually pool 26 is where the Mississippi, the Illinois, the Missouri rivers all converge. That spot is called Grafton, Illinois. It is very prone to flood. Okay. And then up on the Illinois River here, we have LaGrange. All right. That's actually a locking dam. And LaGrange was the pool I studied specifically because it's 45 minutes from my house. How exciting. Okay. And then we got Open River, which is just a very wide section of the river down by Arrow. Okay. So we run the mapper algorithm on our data, right, to learn about the topology of the data. But what do we do after that? Cool, we got this really nice, kind of crazy looking simplicial complex. Not the one I'm showing, but you get a really crazy looking one because our data has about 90,000 points in it. How do we, well, what do we do next? So what, right? So we found a paper studying, which was also released in 2019, studying the guts microbes of people, okay? And what they did was they ran the mapper algorithm, which, for your information, was first published in 2007. So this is all like new stuff. They ran the mapper algorithm on their data for a bunch of different people. And they were actually able to detect ecological states, so to speak, of people's guts. So they were able to tell the progression of the disease that they were measuring for, whether you had the disease or not, whether you had diarrhea. So it was painfully accurate. But that being said, how do they do it? Well, they ran the mapper algorithm, then they calculated the density of each node. Okay. Once they had the density of each node, right? Because remember, the nodes correspond to a group of data points, right? Once they had the density, they made a directed graph from nodes of lower density to nodes of higher density. And then the local maximum to find ecological state, which this makes sense. The ecological state is a bundle of information that persists through time. It makes sense. The most dense ones would represent the ecological state. So this definition makes sense. So moving on, I run that on the whole data set. This is what we get. This is the Mississippi River, okay? And the Illinois River. All right, so we have 3 ecological states that we detected when we do this in one transition state. So a transition node was one that's equidistant between 2 maxima and flows with them. So this one here is actually really nice. So the United States Geological Survey has been doing restoration on the Mississippi River. So Congress demands that Mississippi River has a certain depth in the main channel. But they're trying to restore it to return life to the main channel, the side channels, the backwaters, all those areas. And they've been doing this by putting artificial islands, things in the middle of the river, because that reduces wind fetch. Wind fetch is like just the wind going over the river. There's nothing to stop it. And we're in the Midwest, there's nothing to stop the wind anyway. And that actually makes the river have really big waves. That messes with things. So they've been putting artificial islands there, and they've been actually seeing lots of plant life return and a lot of different pools. So this area right here, when you actually look at the data for it, it's actually water's pretty clean, actually. But then as you go towards the tail, then it gets really bad. So in general, the Mississippi River, the farther south you go, the dirtier it gets. All right, that's because the Midwest is largely agricultural. We have the big basin, all the agricultural products, fertilizers, and runoff, such as phosphorus and nitrogen, flow in the Mississippi River, and that's going to feed algae. Okay, and so the farther south you go, the dirtier it gets. I've actually swam in the Mississippi River when I was up in the cross. Then something got my eye, and that was not fun. But it was clean enough up there. But I don't know if I go swimming in it again. But anyway, we go down here towards the tail. It's really bad. It's very turbid. So let's look at some box plots to show that. All right. State 1, which is that red state in the tail, super high turbidity, right? And state 2 is a little lower. State 3 is very low. So possibly, right? We handed this data off to the ecologists at the United States Geological Survey, and they're still working through it. Possibly, this could correspond to some clean water state in here, or at least a possible substate that's a clean water state, kind of a turbid state. And then it's possible this is the groundwater state, right? Where it's just so bad that not even algae is going. That requires more analysis to actually conclude, but that's the hypothesis we have right now. So, so yeah, more analysis is necessary, like I was saying. But you might notice we have a lot of outliers, right? Because that green state, that big one, 80 or 90% up to date, right? So it might be worth going in there, running the algorithm again to try to break apart different states and study that more closely. That's one thing that's great about the mapper algorithm is that you can look at things with different resolution. Like with river wide, pool wide, I can do it habitat wide in a pool, like the main channel or the backwater, so on and so forth. I can learn different things. Okay, so different resolutions. But with all these outliers, it would probably be worth for us to go look in there and try to divide it up further and see what we can find. Like I said, when I go back, things in the tail tend to be really dirty, but up over here at the very top, there's a very, very clean water. You can see that on this diagram right here. So we were actually, when you look at this, you're able to do things like you can detect what pool you're looking at in this diagram. Because I mean that we didn't encode any pool information in there, but we were still able to extract it. Right. So you can see the nodes were on the last farm, which is where I was, right by La Crosse. Right. See, they got nothing of it next to them. But then when we color by turbidity, see the tail, very high turbidity. All right, but all the way down here, very low turbidity. So turbidity seems to be the driving factor in determining the ecological state. Moving on, here is LaGrange, Illinois, which is really dirty. Okay, so turns out LaGrange has like the highest population density of invasive carp in the world. Invasive carp like to pick up mud, things like that. Those are the carp that you see jump out of the water, you know, when they get scared. And actually, that's right by Beardstown, Illinois. And in Beardstown, I think they have a festival where, like, they go catch invasive carp. Fortunately, they're not very edible. They have a lot of bone in them, so it's just they go. A lot of times they go in with like electric nets, they'll shock the water, and then all the fish come jumping out. It's pretty crazy, but that's probably one of the reasons why the water is so dirty. Invasive carp are actually a huge problem. because we don't want them going in Lake Michigan. Right now in the Chicago area, they have like CO2 nets and electric nets to stop the fish from crossing. But if they get over that and go into cool waters of Lake Michigan, they're going to exponentially grow, and that would be really, really bad. And they are like at the border of Lake Michigan is where they're at right now. They're all the way up in Chicago. So that's not good. This little spot right here, this darker spot, is a only like 1% data when I looked at it, and it's like a local event that happened between 1995 and 1998. I tried looking in the history, like flood. There was a major flood in 1993, but that's not 95 to 98. So I'm not sure what that is, and neither are the ecologists. So that could just be a artifact of the algorithm, or it could be there's more to something there. But that's just that spot right there just has fast moving water. So I could not tell you what that second state is. Continuing on, so some future work could be breaking down that large green state into substates to study it further and glean more ecological information. We could use the period prediction algorithm to look for regime shifts. So regime shift is when the ecological state changes. That's what I'm working on now, is trying to understand that algorithm and apply it to the data set. And then use a topological change form protection algorithm, which is actually what I was working on an hour before this, to aid in search for regime shifts. So what that is you have data coming from one distribution, and at some time, if the distribution changes, how do you detect that change? And I cannot really explain to you that algorithm because I don't fully understand it yet myself. I'm still working. So that's our future work. Last bit is just a thank you for the REU. If you guys ever get a chance, you should definitely do it. Then my mentors, and then my colleagues and co-workers. So there is some legalese right there. There are my citations. QED, that's it. Thank you, guys.
Questions?
That's some things in the chat. Oh. Thank you.
So I've got a question for you. Can you describe just briefly the process of getting into the REU and then become a recommendation base?
Sure thing. So if you're going to apply to an REU, it's good to start thinking about, you're going to use some letters of recommendation. And it's good to think about those people now and then ask them before the term ends. Okay. Because a lot of the due dates are either like January or February, and mostly February and then some in March. Then you have to write some essays, fill out information about yourself, all that. And then and they're very competitive, so you're not guaranteed to get into one. If you do get into one, then you join. Essentially, the first bit of it, first week or two, you will learn any prerequisite information you need. So for us, it was learning about some topology, some algebraic topology. So we actually learned how to compute homology, which I didn't go over, but if anyone wants to see it at the end, I'll show you. Quite complicated, but we learned about that, and then we learned a lot about ecology as well. We had the ecologists we were working with come in and teach us everything we needed to know. And then after that, it was all right, wake up, you go where you're going, and work with whoever your mentor is, your professor, and get to work. And so for me, it was a lot of coding, looking at the diagrams, trying to understand what they mean, reading literature to try to figure out new ideas. It's where we got the densities thing. And then and it was a lot of trial and error because research is never a linear process. You're going to be wrong more often than you're right. That's just the harsh reality of it, but struggle with it. And if you like to struggle, then maybe you should consider grad school.
So how many people were on your team?
Ours had about 10. So there were like 3 people from University of Wisconsin La Crosse. There were actually 2 projects going on in this REU. So it was a big REU, but yeah, there were, I could just actually go back and look.
So it was what, like maybe 15 students split into 2 projects?
Yeah, something like that. Let's see, 1, 2, 3, 4, 5, and then myself. So actually 6. And then there are about 6 together. 7?
So in the algorithm like you were describing with Voronoi squares, and how you guys kind of break up the data to certain time series.
Yep.
I noticed that the subsize you set for that was 250.
Yes.
Do you guys know if there's any like process to getting a good sample size for that set?
Yes. So you're talking about how do I pick 250 as the size?
Correct.
Well, I knew the time series beforehand, so I knew how to construct it for this example. But in reality, I don't know that. So what you do is you actually look at the L1 and L2 norm. You look at the persistence diagram, and remember we had that big bundle of orange, and then just one big orange or two big ones. So what you do is you calculate the L1, the L2 norms, and how far away they are from like line Y equals X, essentially. Yeah, that's what you do. And then after that, you end up deciding, all right, when is it big enough? Then once it's big enough, you have big enough sample size. So you do a bunch of sample sizes, look at the L1 and L2 norms. Once the norm is big enough, you're set. But I go over that, so for the sake of time.
Got it.
Other questions? How about out there? How about our remote audience? Any questions?
I got one.
Okay, well, let's thank Killian. That's a great talk. All right, well, the rumor is we will have the math club again next week. Stay tuned for that. We might have a visitor in California who used to be here. See how that works out for us. Other than that, you all take care and be safe, and we will see you all next time.